Okay, good morning, everyone. As Thibaut mentioned, I'm the Enology professor at Cal Poly, and the idea here that we have with Mark and Thibaut is just to give you just to present a fruitful discussion on phenolics and how we can measure them, but more importantly, how you can make use of them. And in order for me to accomplish that, I would like to give you a brief overview of what we are going to be doing today. First and foremost, here you are going to see three gentlemen, and they are essentially in charge of the three main labs that provide analytical support for phenolics, so you are going to have the chance to interact with them. And from my end, I'm going to give you a primer on phenolics, very simple, and then I'm going to spend 3 minutes just giving you an overview how we can actually measure phenolics, particularly here in the West Coast. But I'm hoping the panelists are going to be able to give you more details, okay? So, I think this is intuitive, but phenolics come from grapes, okay? The accumulation of phenolics starts as early as bloom, so we are talking very, very, very early, okay? And there is going to be a quiz after this presentation. So phenolics get synthesized through the so-called phenylpropanoid pathway. And it's a fairly complex process, but what I want you to know and to see is that the pathway in itself starts with an amino acid called phenylalanine. But there is an enzyme there called phenylammonio lyase. And everything that is highlighted on reds are essentially enzymes. These enzymes, okay, are responsible for the biosynthesis of these phenolics, but more importantly for you, they are under environmental control. The environment controls them. This explains why we see differences in phenolics years in, years out. But more importantly as well for you, cultural practices affect how these enzymes are expressed and thereby the accumulation of these compounds at the vacuole level. Irrigation practices, canopy management, choose of rootstock, clone, all affect the expression of this enzyme. And this is why it's so important to be able to measure phenolics on the fruit. Okay? Now, speaking of the fruit, where phenolics are located, not going to touch base on the pulp. I'm going to focus on starting with the seeds. Now, if you take a look, the seeds on a ripe Cabernet Sauvignon berry at 26 brix, they don't account for much weight. Okay? They do not. They are actually very low in water, okay? And the rest of the composition is essentially phenolic material. What kind of phenolic materials do we have on seeds? First and foremost, we have these compounds, small compounds by the name of monomeric flavantry salts, okay? These monomeric flavantry salts are this doesn't look like a lot, but there is quite a lot, between 0.2 and 0.5 milligrams per berry, okay? Fairly high concentrations. Now, these monomeric flavantry salts are very, 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 very small molecules. Probably you have heard about the term catechin or epicatechin. These are the ones, okay? These are very, 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 very small compounds from the perspective of molecular weight. They are so small, they can creep inside your fungiform taste buds and inside the pore of your taste bud and give you bitterness. Okay, these compounds are bitter. They cannot precipitate tannins. They are not astringent, but they are so small that they can give you bitterness. Of course, the concentration depends upon the variety. Pinot Noir is very well known to have a boatload of these compounds on the seeds. Syrah has much less. Okay, so you all winemakers know that you need to be careful with phenolic extraction on Pinot Noir if you don't want to get these guys. Now, on the seeds, we also have tannins. Okay, there is a lot of tannins on the seeds, between 3 and 5 milligrams per berry. Okay. Now, the point to be made here is that the tannins that we find on seeds are fairly low in molecular weight. Okay. In this particular case, I'm showing you a trimer. Okay. For the most part, the tannins that we see on seeds, they don't exceed a size of 5. So they are fairly low in molecular weight. But keep in mind this thought: they are very, very abundant on a mass basis. There is a lot of these compounds. Okay. Switching gears to the skins. Now, if you take a look at the skins, they account for 10% of the fresh weight, and then you get a little bit excited because we winemakers talk a lot about the skins. Okay, we know that in the skin we have not only phenolic but also precursors and free aromas. Okay, now the bad news for everyone is that most of that 10% is essentially water. Okay, the skin is a very rich tissue on water. The rest is acids and phenolic materials. What kind of phenolic materials? You all have heard about anthocyanins. The point here is for you to realize that these anthocyanins are compartmentalized. They are in vacuoles. They are absolutely isolated. The one that I'm showing you there is malvidin 3-glucoside, the most abundant anthocyanins on grapes and wines by a long shot. But we have others. We have delphinins, cyanin, petunin, peonin, so on and so forth. Okay? Now, this malvidin-3 glucoside happens to be a very abundant anthocyanin, for instance, on Pinot Noir. Okay? And the color of a Pinot Noir looks like the color of a Pinot Noir. Okay? Now, in many vinifera varieties, the position 6 of the glucose is acylated with acetic acid, pecumaric, or caffeic, forming what we know as acylated anthocyanins. Now, these acylated anthocyanins, they don't have the color of malvidin-3 glucoside. They have this color, okay? More purplish, if you will. And the difference in concentration and composition in the anthocyanin content at the skin level explain why the color of a Pinot Noir looks like the color of a Pinot Noir and why the color of a Syrah looks like the color of a Syrah. Okay? That's the color of a Syrah, by the way. Okay? Now, on the skins, we also have tannins. In this cross-section, everything that you see in blue are tannins. Some tannins are vacuolar compounds. They are compartmentalized from vacuoles. Some others are associated with cell walls. Now, the tannins on the skins at a very low concentrations. I mentioned seed tannins between 3 and 5 milligrams per berry. Skin tannins are between 0.5 and 1 milligram per berry. So in Cabernet Sauvignon at ripeness, Washington State, the ratio between seed and skin tannins is 5:1. 5:1. Okay? Now, importantly enough, from a sensory standpoint, these tannins are large, much larger than those on the seeds. Okay? In this particular case, we have a tetramer, but we can have pentamers, hexamers, heptamers, so on and so forth. How high they can be? Up to 80 units. So they can be very large. Now, the larger the molecule, the larger the number of hydroxyl groups protruding out of the structure. And these hydroxyl groups are responsible for reacting with a specific set of proteins in your saliva by the name of proline-rich proteins. These proline-rich proteins give your saliva viscosity and fluidity. When you put them together with tannins, they form a complex. This complex essentially results in the precipitation of the protein out of solution, and you suddenly lost lubrication in your upper lip, sometimes in the roof of your palate, sometimes on the surface of your tongue, and then you get the molecular basis of astringency. Okay? Now, this is what we have on the grapes. You should be aware that as soon as we crush the grapes and we disrupt these vacuoles, everything becomes what chemists call like a chemical train wreck. Things change a lot, and the complexity, the chemical complexity increases, but also the sensory complexity increases. Probably the most important pigments and compounds in terms of being an example of the fact that wine is a chemical train wreck are the so-called polymeric pigments. Probably all of you have heard about these polymeric pigment compounds. And here is a polymeric pigment. Okay, not that you need to know the structure, but the point here is that these polymeric pigments are mostly composed of tannins. Okay, they have anthocyanins, and therefore they have color. Okay. Important chemical and sensory properties of these polymeric pigments. First and foremost, they are resistant to bisulfite bleaching. Second, they are resistant to pH changes. Third, they have positive mouthfeel properties. Think about plush, think about lush, think about run. These are the compounds. Okay? These compounds start their formation soon as you crush the grapes, and essentially the formation never stops. But we know for a fact that the large majority of them forms quite quickly. Okay? This is a wine this is Cabernet Sauvignon, which we decide to macerate for 30 days. And as you can see that after we press at day 30, and from day 30 onwards, actually 1 year, we can see that pretty much we see an increase on polymeric pigments of up to 85%, fast. Okay? And here, what you can see is that we are dividing polymeric pigments in small polymeric pigments and large polymeric pigments. Now, these small polymeric pigments are specific pigments that cannot precipitate proteins, they cannot give you astringency, and these large polymeric pigments are pigments that can precipitate proteins and give you plush astringency. Okay? Now, a problem with polymeric pigments, every single lab and analysis seems to call them in a different way. Okay, you might have heard about the Young and Harveston essay. They call them polymeric pigments, and they come from the summation of small polymeric pigments and large polymeric pigments. But the Australian Wine Research Institute in the early 70s, not just yesterday, the early 70s, developed an essay in which they call them bisulfite-resistant pigments. It's the same. I have here the term bound anthocyanins. I have here the term pigmented tannins. I just want you to know that this is the same. The chemistry in the method might be a little bit different, but we are talking about the same here. okay? Now, let me switch gears briefly to phenolic analysis, okay? And this is just a brief overview. I hope the panel is going to be able to dive in. I actually was doing a little bit of research. We have at least 55 methods that you can use in wine to measure phenolics. Here in the West Coast, I'm just going to mostly cover the two main branches that I believe are relevant here, which are called spectrophotometric methods and HPLC-based methods. Those are what we call direct methods. We are measuring these compounds directly as compared with indirect methods. Now, when it comes to spectrophotometric methods, the take-off message here, I'm not going to dive into chemistry. Phenolics absorb light in the UV and visible range, and we can use that to measure them effectively. There is sometimes overlap within certain phenolic classes, but certain other phenolic classes, such as anthocyanins, absorb 520 nanometers, and we can absolutely quantify them without much trouble. Okay? The phenolic ring absorbs at 280. We can use that absorbance to gauge the total phenolic content. That's easy. Okay? Last but not least, in wine we have tannins. Tannins have the ability to interact with ligands. What are ligands? Ligands from a chemical standpoint are chemical compounds of the fine chemistry that are able to bring down tannins. If they bring them down, we can quantify these tannins. We use two types of ligands. We use proteins, and we use polysaccharides such as methylcellulose. The Adam Harveston assay uses a protein, okay, which goes by the name of BSA, and Jim Harveston has published research that suggests that the tannins that we bring down with BSA are pretty much the same tannins that we can precipitate with our saliva. And this is why these protein precipitatable tannins correlate pretty well with perceived astringency. Okay? Because essentially the amount of the tannin that we are removing is the tannin that potentially react with our salivary proteins. And if you take a look at the pellet that we get with BSA with saliva, it's pretty much the same. What we do is to resuspend the pellet and to measure the tannins that were on the pellet, and we get the protein precipitatable tannins. That's the chemistry. That's not more complicated than that. Now, HPLC-based methods, these obviously require an HPLC. These require sample preparation, okay? And obviously, an HPLC mean cost, we are talking about north of $50,000, okay? Now, the beauty about these methods is that you are actually absolutely measuring these compounds by liquid chromatography. HPLC, by definition, and in the audience there are a couple of wine chemists, they all know what I'm going to say. HPLC chromatography is a good system and analytical method to define monomers, things that are small. When things become polymeric in nature, they cannot interact with the stationary phase in the same way. And it's very difficult to resolve tannins. It's very difficult to resolve polymeric pigments. You can do that, but it's difficult. Okay? Now, when it comes to anthocyanins, you are fine and dandy. I mean, you just stick your wine on an HPLC. Some labs do this, and then you can see the difference in the chromatographic composition of a Syrah, I think. Yes, it's Syrah on your left and a Pinot Noir on your right. If you take a look at the absorbances are different, but also you can see that Pinot Noir lack acylated anthocyanins because Pinot Noir doesn't have acylated anthocyanins. Okay? This is the gold standard for the analysis of monomeric anthocyanins. Okay? Last but not least, we have what we call predictive methods. Okay? I'm going to start by saying the positive things about this method. These predictive methods, we call them indirect methods. Some people is kind of laughing or chuckling, but the reality is they are very useful for practical considerations because they allow you to take decisions and to see numbers on real time. You need to bear in mind that the spectrophotometric methods and HPLC methods are very time consuming and they require a technician and a lab. Okay? Now, for these methods, don't think you don't need a lab. You are going to have to provide certain absorbances. Some labs might call for specific or discrete absorbances. Some labs might call you for the full spectrum scan. Now, what they are going to do with those numbers is they are going to analyze these numbers mostly to multivariate statistics and regression, and they are going to estimate phenolics. Okay? As simple as that. I hope the panels can dive into more detail. Okay? The negative is that they are predictive methods. You are not measuring things directly. The positive is that you can get actually numbers on real time. Okay? And I know many wineries use them with very positive results. Now, the final thoughts here. Obviously, phenolics are relevant from a chemical standpoint, but I guess for the purposes of this audience, phenolics are super important from a sensory standpoint. You should be aware that different methods provide not only different numbers, but more importantly, different interpretations of the same number. Okay, if you are taking a look at protein precipitation by the Adam Harveston assay, the numbers are very, 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 very much lower than the numbers that come from methyl cellulose in the method that come from the AWRI, much lower. Okay, phenolics can be used as a tool. Okay, both in the vineyard and in the winery. Think about deciding when to press. Think about deciding what to do with press fraction. Think about how you can actually maximize can management, punch downs versus pump overs. Think about the potential of doing delestage versus not doing delestage. But for the purposes of this panel, this is what I would like to get you as a take-off message from these three gentlemen is how and when do we need to measure phenolics? And perhaps more importantly, what kind of phenolics do we need to measure to take practical decisions and be able to move forward? This is what I hope with this panel. So this is just my brief introduction. Thank you very much. And with that, I'm just going to invite the panelists here to the stage.